Hi everyone, I am DHARNIA, Assistant Professor in Department of Mechanical Engineering of Arya College of Engineering and IT, Kukas, Jaipur. Today we will learn about the effects of various design and operating variables in the CI engines on the formation of different pollutants. So let's start. There are various operating and design variables which we will consider in our lecture. That there are engine design variables and also operating variables which affects the formation of different pollutants. Like the engine design variables are compression ratio, combustion chamber type, combustion chamber design, injection system. Operating variables like exhaust gas recirculations, engine speed, engine load, and fuel quality. Compression ratio. As you know that diesel engines, the minimum compression ratio that can be used is governed by the ease of engine cold starting ability. For the high speed DI engines, compression ratio of around 16 to 17.5 ratio 1 is used. The turbocharged heavy duty engines employ compression ratio in the range of 13 to 14 ratio 1. Cold starting requirements prevents further reductions in the compression ratio by the use of higher compression ratio, shorter ignition delay period. Delay would result in less overmixing of fuel and air and hence lower HC emissions. Further, the higher combustion temperature obtained at a higher compression ratio tends to increase oxidation of the unburnt hydrocarbons, and at a low compression ratio, a longer delay increases the fraction of fuel burn during the premixed phase, resulting in high peak pressures and temperature, which causes an increase in NOx formations. On the other hand, the increase in compression ratio due to higher combustion temperatures would tend to increase formation of NOx. If the ignition delay is too long, the combustion may begin in the expansion stroke, reducing combustion pressures, and too long an ignition delay leads to lower NOx emissions along with the pure fuel economy or efficiency. Use of a low compression ratio results in too long a delay during engine warm up under cold conditions, and it causes high emissions of unburned fuel, which due to its appearance is called white smoke. A higher compression ratio leading to high combustion temperatures would result in increased chute formations, while on the other hand it increases chute oxidation also. For the obtaining lower particulate and NOx emissions simultaneously, an optimum compression ratio is to be used in CI engine. Fuel injection timing and injection pressure. There is very significant effects of the fuel injection timing and fuel injection pressures on the formations of different pollutants in the CI engines, as the effect of fuel injection timing on NOx emissions from CI engines is quite similar to that of the spark timing in SI engines. When retarding injection timing, as expected, the NOx emission decreases sharply. On the other hand, an increase in smoke results with retarded ignition timing. If the injection timing is retarded too much, HC emissions in naturally aspirated engines also may increase sharply. An increase in injection pressures results in higher NOx and HC. With high injection pressure and higher small nozzle orifices are used The high injection pressures and small nozzle holes give very good fuel atomizations with very small fuel droplets which vaporize rapidly, resulting in low chute emissions. This is the diagram of showing the effects of injection timing on emissions and fuel economy for a heavy duty diesel engine. As we can see that in the chute formations, with the use of retarded injection timing, we will decrease it. There is also increase in HC emission sharply with the retarded injection timing and lower in NOx emissions. And this is the effect of injection pressure on particulate matter emissions for a heavy duty diesel engines. As the injection pressure increases, the particulate emissions decreases. The effect of engine load and speed for developing higher power, more fuel injected in the diesel engine, thereby reducing excess air. On overall fuel air ratio for a direct injection engines shown in the figures, that this is the effect of air fuel ratio and engine load on chute emissions for a DI diesel engines. As the engine load increases, the chute concentrations also increase sharply. With increase in engine load, the NOx and chute emissions increases. With increase in engine load, as the combustion temperature increases and oxidations environment for CO is more favorable, so CO emissions start increasing again and rise sharply as still more fuel is injected to increase engine power output. And at the maximum load, NOx, CO and chute also at their maximum level. However, the HC are reduced with increase in engine load, as higher gas temperature load leads to an increase in the oxidations rate of the unburnt hydrocarbons. The engine, because the ratio of frictions to brake power goes down, interactions among these factors results in lowest value of the brake specific fuel consumptions and optimum value of the brake specific nitrogen oxides and particulate emissions at an intermediate load. The effect of exhaust gas recirculations, it acts as inert diluent and heat sink that reduce the oxygen concentrations during combustions and lower the combustion temperatures. It affects the dilution effect, thermal effect and chemical effect. In the form of dilute effect, it is the reductions in the inlet charge oxygen concentrations, and in the thermal effects, it is the increase in inlet charge heat capacity, and in the form of chemical, the modifications in combustion process as a result of dissociation of carbon dioxide and water vapors. The dilutions effect is the dominant effect in case of diesel engines. The chemical and thermal effects are relatively small in the diesel engines. This is the typical effect on the NOx, CO and HC emissions. As we can see that there is a reductions in using of the EGR in the reductions of NOx emissions and HC emissions. but CO emissions increases if the percentage of EGR rate consumptions increases. So at the rate of 20 to 30% of the EGR consumptions is suitable for the reduction of all three pollutants. So this shows the various brake specific fuel consumptions, brake specific nitrogen oxides, brake specific hydrocarbons, and particulate matter formations with the effect of the engine design variables, fuel injection variables, and operating variables.